All right, let's begin. Thank you very much for attending. It's right now at 2 o'clock, 2:01. I'd like to introduce myself. I'll be your host today. My name is Kevin Cope. I am the Business Development and Application Specialist for Brenntag North America in the water treatment area. And again, would very much appreciate you attending our presentation today. In the past, Brenntag has presented a number of webinars. Most of these, or all of these are located here on the slide. Heavy metals, coagulation, flocculation, successful jar testing, biological treatment, mastering the art of dissolved air flotation, just to name a few. And all of these webinars are available in video form and in also PDF form. And this is the first video. I'm very, very proud to make this announcement that Brenntag webinars have now been certified by the AWT, the Association of Water Treatment, for CEU credits. And what that means is if you have a CWT with the AWT, Certified Water Treater, you can view our webinars, our videos, take a test, complete a test, score an 80% or better, at which point you will obtain a Brenntag certification certificate. You can present that to the AWT for CEU credits, and you can contact me, Kevin Cope, at brenntag.com for all the video links and the exams for the prior webinars that we've done, which we just presented a few moments ago. Today's webinar, once it is completed, will be sent to the AWT Training and Certification Committee, at which time they will review the webinar and certify the webinar for CEU credits. And I will send an email out to everyone attending this presentation today, this webinar today, letting them know when the certification has been, the webinar has been approved, and then send you the test as needed so that you can take the test and then get your certification through the AWT. So we're really excited about that. It's something we've been working on with the AWT. Very proud of that. So let's move forward. Let me talk about today's presenter. The gentleman is Dick McCarthy. I've known Dick for a number of years. He is the Water Additives Manager for the Great Lakes region for Brenntag. He has a degree in Solids and Waste Management for the University of Wisconsin-Stevens Point. I'd like to thank Dick again for his service to the country, 6 years in the Wisconsin National Guard, and 3 years in combat duty in the Iraqi Freedom Campaign. Right now, Dick has a little more than 5 years experience because this was the last time we used Dick as one of our presenters. This is actually Dick's second time. But Dick had 5 years of experience, and it actually is more now, on liquid solid separation. His experiences include polymer usage, sludge dewatering, total suspended solids control, and many others. And we just added this morning, we realized that since the last time Dick has presented, he had a baby daughter. And I think he mentioned her birthday is tomorrow, so it'll be 1 year tomorrow. So with that, I'd like to present Dick McCarthy, who will be doing the presentation today. And Dick, are you ready to go?
Yes, sir. Thank you, everyone, for joining us. As far as what we're going to be discussing today, we're going to start with talking about the characteristics of wastewater. Then we'll get into some of the chemistries used, how you determine a treatment program through jar testing. We'll talk about the different types of clarifiers out there, as well as the checks and controls, and troubleshooting when things go wrong, and maintenance to prevent needing to troubleshoot. And then we'll field questions towards the end. Colloidal suspension. One of the main uses of the clarifier is to separate your fine particles from your clean water. One of the reasons you can't do this on your own without coagulation is flocculation, is something called charge neutralization. This is the fact that many of these particles are like charges, having a negative charge on two ends, keeping the particles from settling out or joining together and settling. The coagulation step will put a positive charge on these negative charges, allowing things to neutralize and settle. Here's a picture representing colloidal suspension. We have two wastewater streams that obviously have some sort of contaminant or substrate in them, and we can't see any pin flock at all. It just looks like one uniform wastewater because of these very fine colloidal particles repelling each other. To give you some actual numbers behind the size of these particles, you have coarse sand up at the top that is very large, about 1 millimeter, and only takes about 3 seconds to settle 1 foot. On the very far end, we have fine colloidal solids that can take over 6 years to settle just 1 foot. The representation of that 6 years ago in 2013, Jennifer Lawrence and Daniel Day-Lewis were the Oscar winners, and Argo was the movie of the year. So coagulation. Coagulation, like we said before, is taking a positively charged coagulant and neutralizing those negative charges. It's always the first step in clarification. All coagulants are positively charged, and they're what create that pin flock, that very small particle size in your wastewater. It'll enhance clarity. You should be able to see some more light pass through, and coagulants are almost always liquids. They can, however, be both organic and inorganic. Some examples of organic coagulants would be epiamines, DADMAX, and starch chemistries. Inorganics are popular ones like alum, ferric sulfate, ferric chloride, ACH, and PAC. They have relatively small molecular weights compared to flocculants, ranging in the 50,000 to 600,000 range. Here we have a visual representation of particles in the wastewater. Each of them will have a negative charge repelling each other with their like charge, preventing any flocculation, pin flock, and settling. When we add our coagulant, since their coagulants are always positively charged, we're going to neutralize that negative charge, allowing the particles to come together and create what we call a small pin flock. After coagulation, we have flocculation. It's the second step, and flocculants, unlike coagulants, can be positive, negative, or neutral charged, and they're used for building and bridging those flocks. Flocculation greatly improves clarity and settling, and they can be emulsions, powders, diluted powders, and most of the time they're white in color. They almost always need to be made down with water before use. In the field, you'll find dilutions ranging from around 0.1% to 2% usually, with 2%, anything above 1% being specialized pumps are usually used because of the high viscosity. And they have very high molecular weights compared to coagulants, over 1 million. So here we have our pin flock, a very small flock inside the jar. We have lots of pin flocks flying around. When we add our polymer, which is a long chain of charges, it will bridge those flocks together, pulling them together to create your large flock, which will more easily settle out. Here we have a visual representation of coagulation and flocculation, where we see small pin flocks are starting to come together, starting to drop out, and we're being able to see that clarity at the top of the water. Here's a video. Our coagulant's already been added. We can see the pin flock. We can see some light coming between the flocks. The flocculant just went in on the right. We start to see more and more clarity as the flocks join together. You'll notice that we don't need very rapid mixing on this. We just have a slow, steady mix. The flocks start to come together. They're increasing in size. We can now see light through the bottom of the jar, see all of the spaces between the flocks. And at this point, we just want to ensure the flocculant's well mixed before we turn off our paddle and allow it to settle out. As you can see, there's greatly improved clarity on the top and the bottom as the flocks remain in suspension. So once it's time to determine a treatment program, you need to bust out your gangster and get your chemical samples ready. One of the most important steps for jar testing is duplicating the system of operation. What this means is whatever process you use to determine your coagulant and flocculant should be a replication of what the current wastewater system is. Meaning, if you allow for 2 minutes of mixing in your coagulant, then the actual wastewater system should have 2 minutes of mixing. For instance, if they only had 10 seconds of mixing with the coagulant before the flocculant hit and you allowed for 2 minutes, this would not be an accurate representation. So we want to determine the best program. We want to choose what's going to be the best chemistries, coagulant, flocculant to use. We want to check the product performance, look to see if there's any different products, such as the ones that they're not using now. And then we can definitely note system adjustments, such as if a customer or a wastewater treatment plant only had 10 seconds of mixing on the coagulant, we could say, you're really going to need 60 or better. Here's the results that we tested and why. And we're going to do that when we demonstrate our program. We want to demonstrate the benefits, capabilities, and then compare it to their current or competitor program. So when we jar test, remember, we're going to test the coagulant first. You always want to check the pH of the wastewater you're doing before you start testing. If that pH is down around 2 or 3, you can add just about any coagulant and flocculant in the world and nothing's going to happen. And then we're going to run these coagulants side by side. We want to see how they're performing visually, and if you're going to test something like TSS, make sure you're testing different chemistries. And if you're testing different chemistries, we want to make sure it's from the same sample. You don't want to pull one sample, test all of your inorganics, dump it, and pull another sample and test your organics 2 or 3 hours later when they could be producing something different in that wastewater stream. Once we have our chemistry coagulant picked out, we want to refine the dosage, and then we want to duplicate the system. Again, you want to make sure what you're doing in your jars is what that plant is doing. Check the pH again at the end. Some inorganics can greatly depress the pH at higher dosages, so you want to make sure you're still in a range with which they can discharge and that your flocculant is still going to work at. And then you're going to jar test more than once. You want to make sure that you're jar testing during different production stages, different times of the year, if allowable. Sometimes you can just chill the water to represent their winter treatment. You also want to make sure that if they're doing cleaning once a week, that you pull a sample during that process or at the end of it, so you know your chemistries are going to work when all of their cleaning chemicals come through. And that goes into asking about the plant operation. You know, do you have regular upsets? Does your production schedule change regularly? And what do those changes look like? So, like we said, coagulation must occur before testing the flocculant. When you're making down your polymers, you want to make sure you make down both cationic and anionic. There are many times when I've been fairly sure a cationic was going to be the right one, and it turns out an anionic actually was correct or better for that situation. So when you're making them down, I always make down several cationics and then just one anionic just to be sure, usually around a 30%. And you want to determine the correct charge, whether that is that cationic, anionic, or non. And then you're going to test various charge densities. Quite often I'll make down a 20, 40, 60, 80% cat and then bracket and then narrow it down from there. And then you're going to test different molecular weights within that best charge density. We want to make sure that our flocks are not going to get sheared in their process. And then when we're making physical observations, we want to look at that flock size. We want to look at the settler rise rates, clarity, any remaining pin flock. And these are all things you can give a 1 to 4 rating on in your notes to go back and look at. So here we have 3 of the main types of clarifiers. We have a rectangular clarifier at the top. We have a circular lower right, and a parallel plate, or otherwise known as a lamella clarifier. So clarifiers have a plethora of applications, from raw water and biological treatment, mine tailings, metal hydroxide creation, color removal. Just about every type of process can have a clarifier on it at some point. So clarifiers are used for separating metals and metal plating and other industrial processes, separating heavy solids in municipal mining and industrial applications. Some have floating scum removals, which are very common in municipal applications to catch grease balls. Clarifiers are kind of an easy, low maintenance, low cost after installation process. So there are some important initial steps that you're going to want to check on before you get into the actual clarifier itself. One of them being equalization. Equalization is a very important step and greatly benefits anyone that installs them for the most part, where we're making sure that whatever our system is treating, it is as blended and it is the same all day, every day as it can possibly be. This allows us to give the most accurate treatment possible. And involved with that is mixing. We want to make sure that everything's getting mixed together and we're getting a uniform stream. pH adjustment, which can also happen in the equalization stage. Like we said before, if your pH gets below 5 or above 10, your coagulant and flocculant probably aren't going to work as well, and you could also violate discharge permits if it makes it through the whole system. Flow control, chemical preparation, we want to make sure if we're using polymers that we're making them down and letting them age. And chemical addition points, like we said, if you can get 60 seconds of mixing between your coagulant and flocculant, that's going to greatly behoove you. So here we have a short video of a plant flock tank, and you can see they've got excellent clarity in between the flock. We're seeing a lot of three-dimensional characteristics, and we can see that it's just working really well. So here we have our rectangular clarifier. You have the rakes on the top to push any fat, oil, grease balls that are floating, and often they will go all the way around to push out the sludge on the bottom. Here we have a side view of a rectangular clarifier. On the left, we have our influent or dirty water coming in, rapid mix where we would add our coagulant, and then slow mix where the flocculators are and our flocculant is being added. It then enters the main portion of the clarifier, solids settle down to the bottom, and the sludge rake pushes it out to sludge disposal, while the cleaner water exits at a higher height in the effluent. And this cutaway just shows you what it would look like if the sludge rake was reversed and the disposal on the other side. Here we have a really excellent picture of a circular clarifier. In the center, in the brown water, we have the dirtier brown water coming in through the main column. And then that clean water comes out at a different height, and it allows the clean water near the mouth there to enter the troughs through holes and exit as effluent. Here we have a reactivator. The influent is coming in on the left. It enters a rapid mix zone in the center where a coagulant can be added. And then that water rises up over the baffles into the slow mix zone where a flocculant would be added, and then sinks down into the sludge contact zone. There we have our sludge blanket. The water moves up into the clean water. Clean water floats to the top where we have our discharge weirs, and then it exits as effluent. And that sludge exits through the bottom through a sludge removal system that the rakes push the sludge to. Here we have just a different version of a clarifier with a slightly different makeup, the same general principle. Everything enters through the middle, rises up, settles, and the clean water exits to the top. Here we have a precipitator version. It's the same basic principle. Sludge settles out, clean water rises. We have a reactor clarifier. And here we have a parallel plate, most commonly called a lamella clarifier. Even though that is just a common brand name of one, it is generally what they're very commonly referred to as. Here we have a cutaway of a parallel plate clarifier. Again, we have the water entering from the left, entering the rapid mix zone, where a coagulant would be added. And here we have a flocculator that is giving that slow mixing that the flocculant likes, preventing shear. The water then enters the baffles, sludge sinks down to the bottom and is removed in the sludge disposal system, while clean water rises to the top and exits across the baffles as effluent. Some of the things that we can check on our clarifier, we want to know what our agitator and rake speeds are. These should generally be the same every day. We want to know what a good working sludge blanket level is, our wasting timer. We want to run settling tests. We want to be able to use a sludge judge or check sludge ports so that we know consistently where that sludge blanket level is at. And then there are some other clarifier control methods we can look at. The agitator speed. So the speed determines both the rate of slurry recirculation and intensity of that mixing. If we get it too high, we could be shearing flock, keeping things suspended. So that optimum rate is going to be different for every facility and every plant, and it's really only through operating experience are we going to know the correct rate. Same thing with the rake speed. We want to know what's generally used and what's generally working so that if we get more solids in or less solids, we know how far to move it away from optimal distance. Sludge blanket level, this is a really important one. It's going to indicate your inventory of solids. If you have too little solids or too much solids, you're going to have a lot of problems. So using things to measure that sludge blanket level is very important, and it's often measured in feet or inches and often from the distance between the top of the water and the top of the blanket. Your wasting timer is going to be another factor that controls your solids inventory. And always remember that short, frequent wasting is much better than long, occasional wasting. Here we have a 5-minute settling test. This is the timed slurry test. There's not necessarily an optimal result for the test. However, it is going to rely on what are your daily operations, how your plant usually behaves, so that you know that you have a number you usually come to. After 5 minutes, we can see that this wastewater has sunk down to about 32 mils, and that's recorded as 32%. Here's an example of a settling test. Like we said before, we know our own plant's optimal rate and the optimal distance that blanket's going to fall. And that indicates that we have a good flocculant feed. And we know that when we do our test, after 5 minutes, that blanket should be down in between our two arbitrary red lines. However, if we do that 5-minute test and it falls outside of that optimal window below it, we know that we're probably overfeeding flocculant and wasting chemical, as well as having too compact and too short of a sludge blanket. If we run our test and we're above that optimal line, then we know our flocculant feed is too light, our sludge blanket's probably too high, and we could be having flock carryover. So a lot of people measure that sludge blanket using what's called a sludge judge. It's a clear tube placed down into the clarifier that allows wastewater and sludge to enter the tube, be drawn up, and then you can then measure how much sludge is in that tube with graduated lines on it. So here we have a picture of an operator holding a sludge judge. They're very long because they have to go into the bottom of the clarifier. And you can see that they just have markings on there about 12 inches apart to indicate the depth. Here you can see a sludge judge goes straight down. We want to make sure it's straight up and down. Hold it there, allowing the sludge to enter, and then we can pull it back out and look at the graduated lines on the sludge judge to determine our blanket depth. For lamella clarifiers, instead of using a sludge judge, what they do is they have ports up the side of it, and you can pull samples from those ports. If you pull your sample and there's sludge in it, you know that there's sludge blanket is there. You go to the next one, if you pull it and it's clean, you know that you're now above the blanket height, and you can then determine where your blanket is on that clarifier. Other control methods, sonar or ultrasonic can be used, optical sludge blanket monitors, and clarifier rake torque monitoring. All these things can get pretty fancy and pretty expensive when compared to a sludge judge. Troubleshooting. So here are some discharge observations and possible solutions. The three main problems: you have pin flock carryover, large flock carryover, and floating flock carryover, and we'll go into those three. Pin flock carryover, especially if you don't have a coagulant, then this may indicate that it's time to get one. Coagulation may be needed to help give everything a charge and allow the flock to grab it. You could also have poor coagulant mixing. There are a lot of people out there, especially as they have a heavier wastewater with anything between 0.1 to 2% solids. They will still think it's okay to just drip or drop a coagulant in there without any baffling or mixing or any even 90-degree turns. And in reality, that coagulant will just sit on top of the wastewater without ever really mixing in. Or it's quite possible they're using the wrong flocculant. They just bought a popular one without doing any jar testing. And instead of anionic, they have cationic or vice versa. Or maybe they just have a popular high charge cationic, when in reality, it's 20% would work much better for them. So pin flock carryover, one of the more operational ways you can fix it is to recycle your sludge, taking it from the final stage in the clarifier and moving it back to the flocculation stage. The old adage, easier to clean dirty water than clean water, works here as well. And you'll recycle some of that sludge and you'll aid in the binding and creating larger flock. Large flock carryover. This is when you have poor sludge blanket control, and it can be too high or too low, but either way, you're getting large flocks coming out your effluent. In this instance, the sludge level is too high, and it's simply just going right out with the effluent. Here on the top, you can see that we've got our ideal good blanket level. And again, this is going to be different for every plant, but this allows the water to come through the sludge blanket, aiding in filtration. If that blanket is too low, we're not getting any benefits from it, and flock will rise right up through it, dirty water, and you'll get large flocks going out with the effluent. Again, this is kind of the same image, but in a lamella or parallel plate frame. Just the sludge level is getting too high. It forces the sludge up through the plates, connects with the effluent, and goes out. Now we have floating flock carryover, which is different than large flock. And what this is usually air entrapment or another contaminant is bringing flock to the surface, and it's literally sitting on the surface of your wastewater. Now you can test to see whether it's air entrapment or oil and grease by agitating it and seeing if it falls out. If it falls out, most likely it was air attaching to the particles. If you agitate it and it still sits right up on the surface, it's most likely oil. For maintenance tips, it's really important to monitor upstream operations closely, and we'll talk a little bit more about that. We also want to use a uniform sampling method. Make sure every operator that takes samples, they're doing it all exactly the same or as close as possible. And we want to use trending data. We want to make sure we're collecting data all the time so that if something happens, we can go back and look at when things started to change and find out what happened then. We want to make sure we act quickly. That if the sludge blanket starts becoming too high, if you don't act quickly, pretty soon you could be violating your permit. And we want to prepare for seasonal changes, such as cold weather can have an effect on our treatment process. It might take more chemistry, and we want to prepare for production changes, especially ones that the plant tells us about. If we know that they're going to change from green beans to sweet potatoes, we want to be ready for that change. Temperature changes, these can have a lot of effects, whether it's creating more biological growth that we need then to clean off the weirs with hoses, or whether it's colder weather allows filamentous bacteria to outcompete our good bacteria, which causes bulking in our sludge blanket and carryover in a higher rising sludge blanket. And we want to make sure when we make these changes, especially if it's a new problem we're trying to fix, that we're only making one at a time so that we know which change it was that made the difference.
Well, Dick, thank you very much. I did an excellent job. Very much appreciate it. We did have some questions come up during the presentation. The first one here is, typically how much sludge would you recycle if you want to do a recycle?
If you can handle it, I think 10% is an ideal number to go back to, filtering it, aiding into stopping that pin flock carryover.
Great, great. Okay, next question. If you do have air or oil in your system, what are some of the things you can do to prevent that or identify it?
I mean, the number one thing is trying to stop wherever it's coming from. If it's air, if you have a leak somewhere that's allowing aspiration, a defoamer should handle the actual problem. If it's oil, especially like in the metal plating industry, we really want to look at separation, not having that oil enter the wastewater at all, whether that's a rope skimmer or just segregating lines. Otherwise, you'll probably have to get some unique chemistry in there to look at breaking the oil and separating it out.
Okay. Another one is, what are some of the things that you consider when choosing a coagulant?
When looking at a coagulant, one of the big things is, cost. Some of the inorganics are going to be pretty cheap. However, a lot of them, like ferric and alum, can also depress the pH and create more solids. I want to know, especially if it's a municipality, I want to know if they have H2S or phosphorus problems. That's going to make a big difference. And then the presence of grease as well. There are a lot of some of the organics that just work a little bit better with fatty or greasy wastewater streams.
Here's another one. What are some of the problems that you've seen with lamellas?
Biological growth can be a big one, especially since lamellas in plating shops, biological activity is not really something they have to deal with. So make sure you're regularly maintaining and cleaning and preventing that biological growth from getting to be the point where it's a big problem.
If you don't mind, I'll add a little personal on the lamellas, is keeping the plates clean. I've seen a lot of times where people just won't clean the plates properly and can really cause havoc with short circuiting through the lamellas. So I'll throw that one out. If you don't mind, maybe two more here. If we need pH adjustment, what would be the best technique?
For pH adjustment?
Yeah.
You want to make sure it's not happening right on top of your coagulant and flocculant. And also, if they just need something really fast, caustic is sulfuric are probably the two best up and down. There are some other chemistries for the metal and plating industry that are really good, whether it's a calcium or magnesium or a blend. It works, can often kind of replace the need for a coagulant in that instance.
And then maybe one more, I can help you with this one too, and then we'll conclude for the day. The question basically is, how do you evaluate old lamella type clarifiers that have been used for a long time that really only have one port? I actually have experience in those areas, and it is very, very difficult. The best way I found was to potentially time your blowdown and see how often you're blowdowning or discharging waste from the lamella, and then correlate that with if you're starting to see higher carryover, and try to say, okay, we need to blow down a little more often, a little less often. But unfortunately, without the ports, it is very, very difficult to really make a determination on where the sludge blanket is in lamella or parallel plate clarifiers. So with that, I think we're going to conclude for today. I see there are a few other questions that we will get to, but let me go to the next slide here, please. And again, I want to thank you all for attending our webinar today. As I stated to begin with, we do now can offer certification through the AWT for CEU credits. This is my name and my email address. Please feel free to email me with requests for the previous webinars that we've done. They've all been approved by the AWT. And again, this webinar will be approved once the video is completed and the audio is completed and submitted to the training committee and the certification committee of the AWT. So again, thank you very much for your day. We very much appreciate your attending, and I look forward to helping you any way we can. Thank you very much. Take care.